The universe is woven together by an invisible spider web. This is the cosmic web, the largest structure known to exist, a vast architecture of dark matter and galaxies spanning the entire cosmos. By the end of this journey, you will understand 28 of its deepest secrets, fundamentally changing your perception of reality. How did this cosmic blueprint first emerge from nothing, and what does its silent structure reveal about our own place within it? What does it feel like to know we are all connected by threads of cosmic darkness? The glittering galaxies we see are merely scattered jewels sewn onto a hidden tapestry. This is the first secret of the cosmic web. Its true skeleton is made of a ghostly substance we cannot see, dark matter. Think of the universe as a grand theater. The stars and galaxies are the actors on the stage, illuminated by brilliant spotlights. But the stage itself, the entire framework that supports the players and guides their movements, remains shrouded in darkness. Dark matter is that invisible stage. It does not emit, reflect, or absorb any light, making it completely transparent to every telescope we have ever built. Yet its presence is undeniable through its immense gravitational pull. This ghostly grip is what first gathered the primordial gas of the early universe, pulling it into the vast filaments and nodes where galaxies would eventually be born. Every majestic spiral, every colossal cluster, is held in place by the unseen hands of dark matter, its gravitational whispers dictating the flow of cosmic history for billions of years. So when you look up at the night sky, you are not just seeing points of light. You are glimpsing the glittering trace evidence of a hidden architecture, a shadowy framework that holds the entire visible universe together. But those brilliant galaxies are not scattered randomly across the void. They are cosmic cities huddled together at the busiest intersections of an invisible highway system. This is the second secret of the cosmic web. The galaxies we celebrate are merely the glowing nodes. The final destination points within a far more immense and active structure. Picture the dark matter filaments as the superhighways of the universe, vast ribbons of gravitational influence crisscrossing the cosmos. Where these highways intersect, they create immense knots of density, gravitational hotspots where matter is pulled in from all directions. It is at these specific crossroads that galaxies are born and thrive, drawing on the abundant fuel funneled toward them by the web. Their majestic spirals and blazing cores are a direct result of their prime location within this cosmic infrastructure. Every movement a galaxy makes, every interaction with its neighbors, is choreographed by the unseen architecture of the web. They are not independent island universes, but deeply connected metropolises whose fates are intertwined by the dark threads that bind them. So when we map the universe and see clusters and superclusters of galaxies, we are not actually mapping the primary structure. We are merely charting the glowing streetlights of a hidden city, tracing the outline of a design so grand it makes every star seem like a single bulb on an infinite Christmas tree. This grand design was first seen not through a telescope but inside a machine. The third secret reveals that the cosmic web was predicted by a computer simulation, a ghostly vision of the universe born from pure mathematics. Decades before our telescopes could ever hope to map its full extent, astronomers were already witnessing its birth within the glowing green lines of their monitors. In the 1980s, researchers like J. Richard Gott III turned to the most powerful computers of their era. They began with a universe of almost nothing, a sparse and nearly uniform sprinkling of digital particles representing the primordial soup of matter after the Big Bang. They programmed in just one single powerful rule, the force of gravity. Then they set the simulation in motion and watched, over billions of simulated years, the simple, relentless pull of gravity worked its magic. Those randomly scattered particles did not stay random. They began to clump and flow, drawn together by their own mutual attraction. Like water droplets coalescing on a spider's web, they traced out an ever sharper pattern. Filaments of matter grew like roots through the darkness. Vast, empty voids ballooned between them, and at the intersections of those filaments where the gravitational pull was strongest, great knots of matter formed, the future homes of galaxy clusters. The simulation did not just create a random scatter of galaxies. It generated a precise, interconnected web, a perfect blueprint for the largest structure in existence. The most astonishing part was that this virtual universe, born from a simple rule, looked exactly like the real maps we would only create much later. It proved that the cosmic web is not a chaotic accident. It is the inevitable, beautiful, and haunting consequence of gravity alone, a signature written into the very fabric of space and time. For a generation of astronomers, the web remained a ghost in the machine, a beautiful theory confirmed only by the digital glow of a screen. The fourth secret is a testament to human persistence, proving that the first direct image of this cosmic architecture would take decades of technological innovation to finally capture. The challenge was immense. The filaments of the web are composed mostly of dark matter, which is invisible, and incredibly diffuse hydrogen gas. This gas is so thin, it emits only a faint, specific wavelength of light known as Lyman alpha radiation. To see it, astronomers needed to do more than just look. They needed to build a cosmic bloodhound, an instrument sensitive enough to sniff out this single, elusive scent across billions of light years. This required telescopes of unprecedented power, equipped with hypersensitive spectrographs that could dissect the light from the darkest patches of space. The quest became a race to detect the whisper of hydrogen gas tracing the invisible bones of the universe. The moment of discovery did not arrive until 2014, a milestone made possible by the combined might of the Keck Observatory and a cosmic trick of nature. Astronomers used the light from a brilliant quasar, a distant cosmic lighthouse, as a backlight. They aimed their instruments not at the quasar itself, but at the seemingly empty space surrounding its path. There, woven between the galaxies, they finally saw it. A faint, greenish glow of hydrogen gas stretched into vast, intricate filaments that matched the computer simulations with breathtaking accuracy. It was not a sketch or a model, but a direct photograph of the universe's fundamental skeleton. For the first time, humanity was not just predicting the cosmic web. We were staring directly at its glowing, gaseous veins, a silent confirmation that the grandest design in the cosmos was real. That first image of the web was more than a confirmation. It was a window back to the very beginning of everything. The fifth secret reveals that the cosmic web is a living fossil, a direct imprint of the universe's violent birth in the Big Bang. To understand how, we must travel back to the first fleeting moments of existence. The newborn universe was not perfectly smooth. It was a searing, dense soup of energy and matter, and it was marred by tiny, quantum ripples, infinitesimal variations in density. Imagine a vast, calm ocean where the surface is almost perfectly flat, but if you could look with infinite magnification, you would see a subtle, random texture like the finest grained sand. These were the primordial seeds, the only imperfections in an otherwise uniform cosmos. For hundreds of millions of years, these ripples were frozen in place, their growth suppressed by the intense radiation pressure of the young, hot universe. But as space expanded and cooled, a fundamental shift occurred. Gravity, the weakest but most persistent of all forces, finally found its opening. It began to pull. Those regions that were ever so slightly denser than their surroundings had a tiny bit more gravitational pull. They started to attract more matter from the less dense regions around them. Over billions of years, this process was a slow, cosmic amplification. A whisper of extra density became a murmur, then a shout. The slightly dense patches grew into vast, sprawling walls. The slightly empty regions emptied out completely, ballooning into the great cosmic voids. The subtle, random texture of the infant cosmos was stretched and sculpted by gravity into the precise, web-like architecture we observe today. Every filament, every node, every vast, empty desert in space is a direct descendant of those initial quantum ripples. This means that when we look at a map of the cosmic web, we are not just looking at the largest structure in the present universe. We are reading a cosmic history book, its first chapter written in the faint gravitational signature of the Big Bang itself. The web is the universe's memory, a permanent record of its own creation, written in galaxies and darkness. That silent history book of the cosmos contains its own empty pages, vast stretches of nothingness that are far more than mere blank spaces. The sixth secret reveals that these cosmic voids are not passive gaps, but are actively, relentlessly growing, pushing the web's filaments apart in a process that will shape the ultimate fate of everything. For a long time, we viewed these voids as simply the empty rooms in the cosmic mansion, the natural result of matter clumping together elsewhere, but we now know they are dynamic engines of expansion. Imagine a sponge heavy with water. If you squeeze the sponge, the water rushes into the densest areas and the air pockets between them grow larger. The universe is behaving in a similar way, but the force doing the squeezing is not a hand, it is dark energy. As dark energy accelerates the expansion of the universe, it exerts a subtle pressure on the cosmic landscape. The filaments and clusters of galaxies, bound by their own powerful gravity, resist this expansion, but the voids, already empty and with incredibly weak gravity, have almost nothing holding them back. So they expand, they stretch, they merge with neighboring voids, creating ever larger deserts of nothingness. This is not a gentle, even process. The growth of these voids actively shoves the cosmic filaments, forcing them into sharper, more defined walls and bridges. The emptiness is actively sculpting the luminous structures we can see. This makes the voids one of our most powerful tools for understanding dark energy itself. By measuring their growth rate, their sizes, and their shapes, we can take the temperature of the universe's expansion. They are a cosmic meter, telling us the strength of the mysterious force that is pulling everything apart. The fate of the cosmic web and of every galaxy within it may not be written in the brilliant clusters, but in the silent, accelerating growth of the voids between them. These cosmic voids are not the only active players in this grand design. The filaments themselves are in constant flowing motion. They are the universe's great conveyor belts, gravitational rivers channeling the raw material for creation. This is the seventh secret. The filaments act as cosmic highways for galaxies, guiding them on billion-year journeys toward the dense, crowded hubs. Picture a great river system on an unimaginable scale. The vast, empty voids are like the high, dry plateaus. The thin, sparse gas and the tiny, dwarf galaxies within them are like scattered raindrops on this high ground. Gravity is the relentless pull of the slope, and the filaments are the deep river valleys carved by that pull. Everything on the plateau slowly, inevitably, begins to flow downhill. Hydrogen gas, the fuel for new stars, streams into these filamentary valleys. Small, isolated galaxies are caught in this current, their trajectories bent toward the gravitational flow. They travel along these dark matter roadways for billions of years, picking up speed as they are funneled closer and closer to their final destination, the brilliant, galaxy-packed clusters at the intersections. This constant influx is what keeps those metropolitan hubs alive and vibrant. The incoming gas provides a fresh supply of fuel, triggering immense waves of new star formation and feeding the supermassive black holes at the galaxy's centers. The galaxies themselves are the migrants, drawn from the quiet countryside of the voids to the bustling cities of the nodes. Without this continuous delivery system, the great clusters would have burned through their fuel long ago, their brilliant lights fading into darkness. The web is not a static sculpture, it is a dynamic, living system, and its filaments are the very arteries through which the lifeblood of the cosmos flows. This faint greenish glow from the cosmic filaments is more than just a ghostly light. It is a cosmic language, a continuous whisper from the most abundant element in the universe, hydrogen. This is the eighth secret, the mysterious Lyman alpha forest, a phenomenon that allows us to read the story written in the web's invisible gas. When astronomers point their most powerful telescopes at the darkest parts of the sky, they do not just see emptiness. They detect a faint, specific shade of ultraviolet light emanating from the hydrogen gas that fills the space between galaxies. This is the Lyman alpha line, the unique fingerprint of a hydrogen atom. But the light we receive is never a single, clean signal. Instead, it looks like a dense forest of individual lines, each one a distinct spike on a graph. This forest is created because the light from a distant quasar, our cosmic lighthouse, must travel through billions of light years of this diffuse intergalactic gas on its way to us. As the light journeys through the cosmic web, hydrogen atoms in the various filaments absorb this specific wavelength, each filament at a different distance and moving at a different speed due to the universe's expansion, takes its own unique bite out of the quasar's light. The resulting spectrum is a barcode of absorption lines, a Lyman alpha forest, where every single line corresponds to a different strand of the cosmic spider web that the light passed through. By decoding this forest, we do more than just map the web's structure. We can take its temperature and measure its density. A sharp, thin absorption line tells us the gas in that particular filament is cold and calm. A broader, fuzzier line reveals the gas is turbulent and hot, likely shaken by the gravitational energy of a nearby galaxy or a cosmic collision. This faint glow is therefore a complete diagnostic tool, transforming the invisible filaments from simple lines on a map into dynamic, living structures with their own weather and history. It is the primary way we can see the universe's skeleton, not just as a static shape, but as a breathing, evolving entity. The fate of a galaxy is written not in the stars, but in its cosmic address. This ninth secret reveals that a galaxy's position within the web fundamentally dictates its very identity, from its shape and lifespan to the potential for life itself. A galaxy living in a dense, bustling cluster at a major intersection faces a life of constant turmoil. The gravitational pull is immense, and close encounters with neighboring galaxies are frequent and violent. These interactions strip away a galaxy's precious reserves of cold hydrogen gas, the raw material needed to form new stars. The result is often an elliptical galaxy, a bloated, spherical swarm of old, red stars, a retired giant whose days of vibrant star formation are long over. Its planetary systems, if any survive the gravitational chaos, would be ancient and quiet. Now, imagine a galaxy born along a quiet filament, a cosmic countryside road. Here, the gravitational environment is far more serene. It can hold onto its gas, allowing it to slowly and steadily form new stars across billions of years. This is the perfect nursery for a majestic spiral galaxy like our own Milky Way, with its graceful arms and active core. The stable, steady supply of fuel allows for generations of stars to be born, and with them, the heavy elements necessary to build rocky planets. In the most isolated locations, deep within the silent voids, a galaxy is truly alone. Cut off from the web's delivery system, it has little access to fresh gas. Such a galaxy is often a small, faint, and irregular dwarf, its star formation starved into a near halt. It is a cosmic hermit, aging slowly in solitude, its potential for complex planetary systems severely limited. So the grand architecture of the cosmic web does more than just arrange galaxies in space. It scripts their entire life story, determining whether they will be vibrant spiral cities, retired elliptical giants, or quiet dwarf hermits, simply by virtue of where they were placed at birth. This grand design, for all its beauty, presents a profound cosmic conundrum. The 10th secret of the cosmic web is that its observed architecture sometimes directly challenges our most fundamental understanding of physics. The standard model of cosmology, known as lambda cold dark matter, has been our guidebook to the universe for decades. It is a powerful recipe that combines the known particles of matter, a specific type of slow-moving dark matter, and the force of dark energy to explain cosmic evolution. Yet when we compare this model's predictions to the actual, observed cosmic web, we find subtle but critical mismatches. The precise spacing of the vast voids, for instance, or the exact thickness and distribution of the filaments, do not always align perfectly with what our best simulations tell us should be there. It is as if we have the blueprint for a cathedral, but when we build it, the arches are a slightly different shape and the pillars are not quite where the plans said they would be. These are not mere details, they are potential cracks in the foundation of modern physics. This forces scientists to confront a radical possibility. Perhaps our understanding of gravity itself is incomplete. Einstein's theory of general relativity has passed every test with flying colors, from explaining the orbit of Mercury to predicting gravitational waves. But does it hold true across the largest scales of the cosmos, across these billion light-year stretches of emptiness and density? Some physicists are now exploring modified theories of gravity, ideas that tweak the rules ever so slightly to see if they can better explain the web's intricate structure without the need for so much invisible dark matter. Alternatively, the problem might not be gravity, but the dark matter particle itself. What if dark matter is not cold and slow, but slightly warm, moving just fast enough to alter how the first structures formed? Or what if it can interact with itself through some unknown force, creating a subtle pressure that changes how filaments condense? Each observation of the cosmic web is a new data point in this grand investigation, a clue that pushes us to refine or perhaps even revolutionize our core theories. The web is not just a structure to be mapped, it is the ultimate experimental laboratory, testing the laws of physics on a canvas of unimaginable scale. This grand cosmic blueprint is far from complete. The 11th secret reveals the cosmic web as a living, evolving entity, still under construction after nearly 14 billion years. New observations with the most advanced telescopes show its filaments stretching, merging, and even collapsing in real cosmic time. We are witnessing the slow-motion assembly of the largest structure in existence. Think of a city that is never finished, where new highways are constantly being paved and old neighborhoods are being reshaped. On the cosmic scale, this is happening with the vast filaments of dark matter and gas. As dark energy continues to push the universe apart, it stretches these filaments, making them longer and thinner. At the same time, gravity is relentlessly pulling matter along these rivers, causing some smaller filaments to merge into larger, more massive strands. In other regions, entire sections of the web can collapse as the gravitational pull from a massive galaxy cluster wins a local tug of war, drawing a filament inward and feeding the growing behemoth. This is not a gentle process. It creates colossal shock waves that heat the gas within the filaments to millions of degrees, a turbulent weather system on a galactic scale. This ongoing construction directly shapes the universe's future. The rate at which gas is funneled into the great clusters determines how many new stars they can form and for how long. The stretching of the filaments dictates how isolated the cosmic voids will become, potentially stranding entire galaxies in the deepening quiet. We are not looking at a finished portrait of the cosmos, but a single frame in a movie that is still playing. The universe is still weaving its own tapestry, and we are here just in time to watch the threads being drawn. The glittering stars and galaxies we so admire are cosmic liars. They represent only a tiny fraction of the universe's normal matter. This is the 12th secret of the cosmic web. The majority of the atoms that make up everything we see and touch are not in these brilliant islands at all. They are hidden in plain sight, suspended in the vast, invisible filaments of the web itself. For decades, astronomers faced a baffling cosmic accounting error. When they added up all the normal matter, the protons and neutrons known as baryons, found in all the stars, galaxies, and visible gas clouds, more than half of it was simply missing. It was a profound mystery, as if you took a census of a country and discovered that most of its population had simply vanished. The answer was not in the bright cities, but in the dark countryside between them. The missing matter was hiding in the filaments, not as cold gas, but as a searing, diffuse plasma known as the WIM, the warm-hot intergalactic medium. This is a gas so incredibly hot, reaching millions of degrees, that it does not emit visible light. It is a thin, superheated fog woven through the dark matter skeleton, so tenuous that a single cubic meter of it might contain only a few atoms. Detecting this ghostly plasma required a new kind of vision, the ability to see in X-rays. Powerful space telescopes like XMM Newton and Chandra became our cosmic thermometers, scanning the seemingly empty spaces between galaxies. They looked for the faintest X-ray glow, the signature of atoms so violently agitated by the web's immense gravitational forces that they radiate at these high energies. They also used a clever trick, watching how the light from distant quasars dimmed at very specific X-ray wavelengths as it passed through these filaments, revealing the absorption fingerprints of oxygen and other heavy elements floating in the hot fog. This discovery solved the mystery of the missing matter. The grand architecture of the cosmic web is not just a skeleton of dark matter, it is also the primary reservoir for the normal atoms that build planets and people. We are not just connected by darkness, but by a faint, hot wind of primordial atoms, a sea of potential that stretches across the entire universe. The invisible filaments of the cosmic web hold a tremendous weight, a mass so immense it literally bends the fabric of reality around it. This profound gravitational influence gives us our most powerful tool for studying its hidden structure, a technique known as gravitational lensing. Think of space-time as a vast, taut rubber sheet. When you place a heavy object on it, the sheet warps and stretches. Now, imagine a beam of light traveling across this warped sheet, its path forced to curve around the heavy object. This is the essence of gravitational lensing, a direct prediction of Einstein's theory of general relativity. The dark matter filaments, though invisible, are those heavy objects on the cosmic rubber sheet. Their collective gravity creates a subtle, smearing distortion in the light from galaxies billions of light years behind them. It is not the dramatic, ring-like lensing caused by a single massive galaxy cluster, but a far more delicate effect called weak lensing. To the untrained eye, the thousands of distant galaxies in a patch of sky might look perfectly normal, but to astronomers, their shapes tell a secret story. Without the warping presence of a filament, the orientations of these background galaxies should be random, like confetti sprinkled on a floor. However, the filament's gravity systematically distorts their images, stretching them in a coherent, arc-like pattern that traces the filament's hidden outline. By meticulously measuring the subtle, statistical alignment of millions of these distorted galaxies, scientists can perform a kind of cosmic cartography. They can create a detailed mass map of the intervening space, literally weighing the dark matter filaments by the way they bend the light passing through them. This allows us to see the unseen, confirming not only the existence of the web skeleton, but also measuring its density and distribution across the cosmos. It is a remarkable feat, using the distorted light of ancient galaxies to illuminate the dark backbone of the universe. The silent, accelerating growth of the cosmic voids is a direct message from the universe's most mysterious component. This 14th secret reveals that the large-scale geometry of the cosmic web itself holds vital clues to the nature of dark energy, the force driving the cosmos apart. To understand how, we must look beyond individual galaxies and see the web as a single, vast instrument. its expansion is not uniform like a balloon inflating evenly. Instead, dark energy exerts its influence most strongly on the emptiest regions, causing the voids to stretch faster than the dense filaments. This differential expansion leaves a distinct fingerprint on the web's architecture. Imagine a grid of dots painted on a rubber sheet. If you stretch the sheet evenly, the dots simply move apart. But if you pull harder on certain areas, the entire grid will distort, creating specific patterns of strain. The cosmic web is that grid on a universal scale. By meticulously mapping the precise shapes of the voids and the angles at which the filaments connect, scientists can measure this cosmic strain. They can calculate the rate at which the web's own skeleton is being pulled taut. The exact statistics, the specific clustering pattern of galaxies across billions of light years, act as a cosmic speedometer for the universe's acceleration. A web that is stretched into a particular configuration with voids of a certain characteristic size points to a dark energy that behaves in one specific way, perhaps with a constant strength over time. A different pattern with faster growing voids and more sharply defined filaments might suggest a dark energy that is evolving, growing stronger or weaker as the universe ages. Each new three-dimensional map of the cosmos is not just a pretty picture, it is a data set that constrains the possible identities of this phantom force, ruling out some theories and giving weight to others. The grand design we see is therefore a dynamic record of the invisible push that is shaping our ultimate fate. That faint, ghostly skeleton of the web holds an even deeper resonance, a frozen echo from the universe's first moments. The 15th secret is that the cosmic web has a distinct sound, a fundamental note imprinted into its very structure. This cosmic hum is known as baryon acoustic oscillations. To understand it, we must go back to the universe's infancy, a mere 400,000 years after the Big Bang. The cosmos was a searing, opaque plasma, a roiling soup of atomic nuclei, electrons, and light. In this dense fluid, gravity was constantly trying to pull matter together into clumps, but it had a powerful opponent, radiation pressure. Imagine a pot of water at a rolling boil, with bubbles of steam constantly forming and being pushed apart by the churning energy. In the early universe, a region of slightly higher density would begin to collapse under its own gravity. But the intense radiation pressure would fight back, creating a colossal spherical sound wave that blasted outwards through the plasma. This wave traveled at a significant fraction of the speed of light for nearly 400,000 years, pushing matter outward in a great shell. Then, in a flash, the universe cooled enough for atoms to form. The fog cleared, the plasma vanished, and the light was set free in what we now see as the cosmic microwave background. The sound waves were instantly frozen in place, their journey halted. The result was a universe where matter was not randomly distributed. There was a slight but statistically significant preference for galaxies to form at a specific distance from one another, a distance equal to the radius of that ancient sound wave. This distance, about 500 million light-years, became a permanent standard ruler etched into the fabric of the cosmos. Today, when astronomers create three-dimensional maps of millions of galaxies, they do not see a random scatter. They detect this faint, overlapping pattern of spherical shells, like the ripples from countless stones thrown into a pond, all frozen at the same moment. By measuring the apparent size of this standard ruler at different distances, and thus different eras of cosmic history, we can precisely measure how the universe has expanded over billions of years. It is the most reliable measuring tape we have for the cosmos, a fossilized sound wave that allows us to hear the echo of creation in the silent arrangement of galaxies. This cosmic hum, this frozen sound wave, is the fundamental rhythm from which all structure is born. Every galaxy, every star, and every planet owes its existence to the gravitational blueprint of the cosmic web. It is the ultimate source, the foundational architecture from which all smaller structures emerge. Think of a mighty river delta. the initial flow of water carves out the primary channels, the largest arteries that define the entire landscape. From these main channels, smaller tributaries branch off, and from those, even smaller streams, until finally, the water reaches the individual grains of sand on the riverbank. The cosmic web operates on this same principle of hierarchical growth, but on a scale that defies comprehension. It began with the grandest divisions, the first vast walls and filaments defined by the primordial ripples. Gravity then went to work within this network, focusing its power. The intersections of the largest filaments, the densest nodes, became the cradles for galaxy superclusters, the largest gravitationally bound structures we know. Within these superclusters, smaller knots along the filaments themselves collapse to form rich galaxy clusters. And within those clusters, individual galaxies like our Milky Way finally coalesced, their own spiral arms and central bulges, a miniature echo of the filamentary structure that gave them birth. This process continues all the way down. The gas that flows into a galaxy along these cosmic highways fragments further, collapsing into giant molecular clouds, which then break apart to form individual star systems and their planets. The very solar system you call home is a product of this immense chain of causality, a final, intricate detail in a pattern that was set in motion when the universe was less than a second old. We are not just living in a universe that contains a cosmic web. We are living inside one of its tiniest, most delicate threads, a direct and inevitable consequence of its silent, gravitational design. This superheated fog of missing matter presents a monumental challenge. Pinpointing the exact temperature and density of the warm-hot intergalactic medium is one of the most difficult tasks in all of modern astronomy. The problem is one of cosmic subtlety. This gas is so incredibly diffuse that a single filament spanning millions of light-years might contain less total mass than a single large galaxy. Its heat is not a fierce, blazing fire, but a lukewarm, tenuous warmth spread across a staggering volume of space. Trying to detect it is like trying to spot a single, warm breath on a cold, windy day from 1,000 miles away. The faint X-ray glow it emits is often drowned out by the brilliant emissions from nearby galaxies and quasars. To make matters more complex, the WIM is not a uniform blanket. It is a chaotic and varied medium with temperatures ranging from 100,000 to 10 million degrees Celsius. Some filaments might be relatively calm and cool, while others are turbulent rivers shaken by gravitational shocks, superheated to extreme temperatures. Mapping this intricate thermal landscape requires more than a single tool. It demands a symphony of observational techniques. Astronomers must combine the faint X-ray glow with the subtle dimming of ultraviolet light from distant quasars, and even the way this hot gas slightly distorts the cosmic microwave background. Each method provides a different piece of the puzzle, a glimpse into a specific temperature range. Solving this thermal mystery is crucial because the heat of the WIM tells us the story of its life. How much energy did it absorb as it was funneled into the filaments by gravity's relentless pull? How violently was it shocked and compressed as galaxies collided and clusters merged? The temperature of this ghostly plasma is a direct record of the violence and drama that shaped the cosmic web, a thermal echo of the universe's turbulent history. These gravitational rivers do more than just build galaxies, they also awaken the monsters lurking within them. The 18th secret reveals that the cosmic web is the ultimate feeding ground for supermassive black holes, channeling fuel directly into their invisible mouth. At the center of nearly every large galaxy, including our own Milky Way, lies one of these cosmic behemoths, an object so dense that not even light can escape its grip. For most of their lives, these black holes are quiet and dark, slumbering giants. But when a fresh supply of gas is delivered, they can awaken with a ferocity that outshines an entire galaxy. This is the birth of a quasar or an active galactic nucleus, the most persistently luminous objects in the universe. The question has always been, where does this immense feast come from? The answer lies in the web's grand infrastructure. The same dark matter filaments that guide galaxies also funnel colossal reservoirs of cold hydrogen gas on a direct course toward the galactic center. It is a targeted delivery system of cosmic proportions. Picture a vast river system converging on a single, bottomless drain. The gas flowing along the invisible magnetic highways of the filament loses its angular momentum as it spirals inward. It piles up in a furious, glowing disk just outside the black hole's event horizon, heating to millions of degrees through friction and gravitational stress before vanishing forever. This process transforms gravitational potential into pure, brilliant radiation. Without the steady, large-scale supply from the cosmic web, these supermassive black holes would remain starved and dormant. Their brilliant outbursts are not random acts of cosmic violence, but the direct result of their privileged position within the universe's largest structure. They are the final destination for the cosmic currents that have flowed for billions of years, proof that the web connects the grandest scales to the most extreme phenomena. The true scale of the cosmic web defies every human sense of distance. A single one of its filaments, a mere thread in the grand tapestry, can stretch for hundreds of millions of light years. To even begin to grasp that, consider a journey at the speed of light, the fastest possible pace in the universe. You could travel from Earth to the Sun in just over 8 minutes. To cross our entire Milky Way galaxy would take you 100,000 years. Now, point your ship along one of these cosmic filaments. You would race for 100 million years, and then another 100 million, and you would still be traveling along that same single thread, with countless others branching off into the darkness around you. The entire structure, this interconnected lattice of filaments and voids, spans the entire observable universe, a volume so immense it contains billions of galaxies. Our entire local group of galaxies, including Andromeda, is just a tiny, insignificant knot in one minor filament. Our most powerful telescopes can only ever map a fraction of its full extent, a tiny window into an architecture whose true size may be infinite. This scale is not just large, it is ontologically different from anything we are built to understand. It reveals that we are not merely small, we are a temporary pattern of stardust woven into a design whose edges we cannot see and whose age we can barely measure. The awe you feel is not an exaggeration. It is the only rational response to a structure that makes a galaxy seem like a single grain of sand on a beach that has no end. This intricate web of galaxies and dark matter feels uniquely cosmic, yet its blueprint appears everywhere we look. The 20th secret reveals that the filamentary pattern of the cosmic web is a universal one, a fundamental architecture for complex systems across nature. Our own brains provide the most intimate example. A single human neuron with its branching dendrites and long axon looks uncannily like a miniature galaxy connected by a thin filament of dark matter. Scale this up to the entire brain, and you see a neural network, a web of interconnected cells where clusters of neurons, like galactic nodes, are linked by fibrous pathways that carry electrical impulses instead of gravity. The structure is the same, a network optimized for efficient communication. This pattern repeats in the systems we build. The physical backbone of the internet, the vast array of fiber optic cables spanning the globe, traces out a web of its own. Data hubs in major cities act as dense nodes, connected by high-capacity lines that channel information across continents, a luminous echo of the cosmic highways. Even our social interactions form an invisible web, where tightly knit communities are linked by weaker ties to other groups, creating a vast human superstructure through which ideas and influence flow. From the microscopic to the cosmic, this recurring motif suggests something profound. A web-like network may be a natural, optimal state for any system where resources, whether they are information, matter, or energy, need to flow efficiently between connected points. It is a pattern that emerges from the mathematics of connectivity itself. The universe did not invent the web, it simply obeys a deeper law of organization, one that writes the same signature across the fabric of reality, from the synapses in your mind to the vast, dark spaces between the galaxies. The recurring pattern of the cosmic web might be more than just a natural shape. It could be a cosmic fingerprint, a scar left by a far more profound connection. The 21st secret ventures into the most speculative edge of cosmology, where the web is not merely a structure within our universe, but a potential gateway to others. Some of the most ambitious theories in physics, like string theory, suggest that our universe is not alone. It may be one bubble in a vast, frothing cosmic foam, a single page in an infinite book of parallel realities. If this multiverse is real, a pressing question emerges. Where would these universes touch? The immense gravitational nodes of the cosmic web, those dense clusters where thousands of galaxies are crushed together by dark matter, are prime candidates. In these regions, the fabric of space-time is stretched and warped to its absolute limit. It is conceivable that under such extreme conditions, the boundaries between our universe and a neighboring one could become thin, perhaps even forming a tenuous bridge. Another possibility lies within the filaments themselves. These cosmic highways are not solid tubes, but flowing rivers of gravitational influence. Some models propose that the fundamental strings of reality, vibrating at the heart of all matter, could become entangled across these vast distances, creating a quantum link to another dimension entirely. It is a staggering thought. A journey along one of these dark matter filaments might not just take you to another galaxy, but to an entirely different cosmos with its own laws of physics. Of course, this idea remains entirely theoretical, a ghost in the equations of theoretical physicists. We have no observational evidence, no instrument that can peer beyond the edge of our own universe. Yet the mere possibility reframes the entire cosmic web. It transforms from a beautiful structure into a potential architectural blueprint, a map not just of what is, but of what could be connected. The web's grand design might be the ultimate hint that our reality is far vaster and more mysterious than we ever dreamed. Our own Milky Way galaxy occupies a quiet suburban street in this immense cosmic metropolis. While we are part of a vast supercluster known as Laniakea, a Hawaiian word meaning immense heaven, our specific location is far from the bustling downtown. Laniakea is a sprawling continent of galaxies, 100,000 strong, all flowing toward a hidden gravitational center called the Great Attractor. Yet within this vast supercluster, the Milky Way resides on a minor filament, a celestial side road that winds its way through the outskirts. This cosmic backwater address has fundamentally shaped our existence. Had our sun been born in a dense cluster at a major node, the night sky would be a brilliant, crowded tapestry filled with the glaring light of countless neighboring stars. The profound darkness that allows us to see the depths of the universe would be replaced by a permanent, luminous haze. More critically, the gravitational turmoil of such a dense environment would have likely prevented the formation of our stable solar system or torn it apart shortly after its birth. The gentle, steady evolution that allowed life to arise on Earth is a direct benefit of our quiet galactic neighborhood. Our remote position also frames our entire view of the cosmos. From our quiet street, we can see the grand design of the web stretching away from us, its architecture clear and unobscured by local brilliance. We are not at the center of the action, but our peripheral vision grants us a unique and privileged perspective on the universe's largest structure. Our cosmic humility is not just philosophical, it is geographical, written into the very address of our galaxy. The vast cosmic architecture we now take for granted was not the result of a deliberate search, but a breathtaking surprise. Secret 23 reveals that the discovery of the cosmic web was a complete accident, a pattern that emerged from the data when astronomers were looking for something else entirely. Throughout the 1970s and 80s, teams were engaged in the monumental task of conducting the first large-scale redshift surveys. Their goal was not to find a web, but simply to measure the distances to thousands of individual galaxies to create a three-dimensional picture of our local universe. They would point their telescopes night after night, collecting the faint light from galaxy after galaxy, painstakingly measuring their redshifts to calculate how far away each one was. They then began the tedious work of plotting each galaxy's position on a three-dimensional map, a single point of light at a time. At first, it was just a growing collection of dots, a scatter of cosmic cities. But as more and more points were added to the chart, a whisper of something began to appear. The galaxies were not randomly sprinkled. They seemed to be lining up, forming faint connected chains. Vast empty regions began to take shape, surrounded by these thin walls of light. The researchers were stunned. They were not looking for a pattern, but the pattern found them. It was like carefully stitching individual stars onto a black cloth, only to step back and realize you had unknowingly embroidered a continent. The first maps, like the famous CFA2 survey, revealed a universe that was shockingly structured, a spongy, cellular architecture that they named the cosmic web. This was not a clean, theoretical prediction confirmed by observation. It was a raw, empirical fact staring back at them from their own data, a fundamental truth about the cosmos that had been hidden in plain sight until the moment we learned how to see in three dimensions. It was a humbling reminder that the universe often reveals its greatest secrets not when we are seeking them, but when we are simply looking with patience and with wonder. This vast map of the cosmos is far more than a spatial diagram. It is a living chronicle of time. The 24th secret reveals that the cosmic web is a functional time machine, allowing us to watch the universe grow up by simply looking outward into the depths of space. Because light takes time to travel, every glance at a distant object is a glimpse into the past. When we train our most powerful telescopes on galaxies 10 billion light-years away, we are not seeing them as they are today, but as they were 10 billion years ago when the universe was in its turbulent youth. By mapping the web at these incredible distances and comparing it to the mature, local web we see around us, we are effectively scrolling through the universe's family photo album. The differences are dramatic. In the early universe, the web was a faint, fuzzy sketch. The filaments were thicker, more diffuse, and filled with turbulent, raw gas. Galaxies were smaller, more chaotic, and clumped tightly along these primordial threads, like beads on a string that had not yet been pulled taut. The cosmic voids were smaller too, mere pockets of emptiness beginning to form between the first structures. There was a frantic energy to it all, a universe under construction. Now compare that to the local modern web. The filaments have been sharpened and refined by billions of years of gravity's relentless work. They are thinner, more defined, and have channeled vast amounts of matter into the nodes, building the immense galaxy clusters we see today. The voids have ballooned in size, merging and stretching as dark energy pushes them apart, forcing the web into a clearer, more distinct pattern. It is the difference between a child's rough crayon drawing and the precise lines of an architect's blueprint. This direct observation of cosmic evolution is our only way to test the grand story of our universe. Does the web thicken and sharpen at the rate our models predict? Do the voids grow as quickly as we think they should? Each deep field image from the James Webb Space Telescope is not just a pretty picture, it is a new data point in this billion-year timeline, a single frame that helps us reconstruct the entire movie of cosmic history. We are not just mapping space, we are witnessing the slow, majestic maturation of reality itself, watching the universe learn to weave its own tapestry. Even the empty spaces between the galaxies are not truly empty. A more recent discovery has revealed that the cosmic filaments are threaded with immense, invisible magnetic fields, a ghostly force woven through the universe's skeleton. These fields are incredibly weak, 1,000,000 times fainter than Earth's own magnetic field, yet they stretch for hundreds of millions of light years. Their origin is one of cosmology's great puzzles. They were not born with the Big Bang, but were forged in the turbulence of the young universe. As the first galaxies and stars ignited, they spewed out colossal winds of charged particles. Supernova explosions acted as cosmic bellows, blasting magnetized material out into the intergalactic voids. This magnetized plasma was then swept up and stretched by the same gravitational currents that shaped the web, painting the filaments with these vast, faint fields. Once established, these magnetic fields begin to influence everything that moves through them. Charged particles like protons and electrons are forced to spiral along the magnetic field lines as they travel. This can funnel and guide the flow of intergalactic gas, subtly shaping how matter accretes onto galaxies and potentially even influencing the direction of powerful cosmic jets erupting from supermassive black holes. The presence of these fields is a cosmic history book for magnetism itself. By measuring their strength and orientation in the oldest, most pristine filaments, we can trace them back to their sources, understanding when the first stars began to seed the cosmos with this invisible force. They are a silent, pervasive reminder that the universe is not just held together by gravity, but is also shot through with the subtle, ordering influence of magnetism, a fundamental force now seen to operate on the very largest of scales. The quiet hum of the cosmic web holds a long-standing whisper of a problem, a mismatch between theory and observation that has puzzled astronomers for decades. Our most successful model of the universe predicts that large galaxies like our Milky Way should be surrounded by a vast swarm of smaller dwarf galaxies, hundreds of them, like moons orbiting a giant planet. Yet when we look, we find only a handful. This is the missing satellite problem, and its solution may be woven into the very fabric of the web itself. Where did all these tiny galaxies go? The answer might not be that they are missing, but that they were never allowed to form in the first place, their potential snuffed out by the environment of the early cosmic web. In the universe's youth, the web was a more violent and radiant place. The first stars and galaxies to ignite did so along the densest filaments, flooding the entire cosmic structure with intense ultraviolet radiation. This cosmic background of UV light acted like a universal sterilizer. For a small, fragile cloud of gas trying to collapse into a dwarf galaxy, this radiation was a relentless foe. It would heat the gas, preventing it from cooling down and condensing enough to form stars. The tiny galaxy was stillborn, its potential forever locked away in a warm, diffuse haze. At the same time, the web's powerful tidal forces were at work. As dark matter clumps and gas streams flowed along the filaments, the immense gravitational shear could literally pull a budding dwarf galaxy apart, stretching its gas into ribbons before it ever had a chance to ignite. It is a cosmic filter where the large-scale architecture of the universe itself decides which seeds will grow into glittering islands and which will remain as dormant dark matter ghosts. So the missing satellites are not a failure of our models, but a profound clue. They tell us that the cosmic web is not a passive stage, but an active participant in galaxy formation. Its ancient light and gravitational tides sculpting the population of galaxies we see today, leaving only the strongest to survive. Our current maps of the universe are like the first, grainy photographs of a distant shore. The next generation of observatories will bring that shore into hyper-realistic focus, transforming our view from a faint sketch into a high-definition movie. The James Webb Space Telescope, with its unparalleled infrared vision, is already peering into the deepest reaches of space and time, watching the first delicate threads of the web begin to form. It sees through the cosmic dust that has hidden the earliest galaxies, revealing exactly how they lit up along the dark matter filaments in the universe's infancy. But Webb is just the beginning. Soon, the Vera C. Rubin Observatory will begin its 10-year survey of the entire southern sky, its massive camera capturing time-lapse images of billions of galaxies. This will not be a static snapshot, but a dynamic sensors, allowing us to trace the subtle gravitational distortions of weak lensing across the entire local universe. It will weigh thousands of dark matter filaments simultaneously, creating the most precise mass map of the cosmic skeleton ever made. Then comes the Square Kilometre Array, a radio telescope of staggering sensitivity. It will do what was once thought impossible, mapping the distribution of neutral hydrogen gas across the primordial universe. It will essentially take a three-dimensional MRI scan of the cosmic web in its adolescent stages, revealing how the faintest, most diffuse filaments channeled gas to fuel the growth of galaxies. Together, these instruments will act as a single, coordinated instrument of discovery. They will measure the temperature and turbulence of the WIM with unprecedented accuracy, hunt for the faintest dwarf galaxies to finally solve the missing satellite problem, and use the cosmic ruler of Baryon acoustic oscillations to measure the expansion of the universe with pinpoint precision. They are not just bigger telescopes, they are keys designed to unlock the final doors to the web's deepest secrets, showing us the universe's grand design in a clarity we have only ever dreamed of. The final secret is not about the web itself, but about us. This grand cosmic architecture fundamentally redefines our place in the universe. We are taught that we live on a planet orbiting a star inside a galaxy. While true, this is a staggeringly incomplete picture. The reality revealed by the cosmic web is far more profound and humbling. Our Milky Way galaxy is not a solitary island. It is a single, luminous thread woven into a tapestry of incomprehensible scale, a tapestry whose patterns were set by the first tremors of the Big Bang and whose evolution is choreographed by dark matter and dark energy. This means you are not merely a resident of a solar system. You are a living part of the largest structure known to exist. Every atom in your body was forged in a star that itself formed from gas channeled along these cosmic highways. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was once scattered across the intergalactic medium, drawn into the Milky Way by the same gravitational currents that shaped the web. You are not just in the universe is in you, and the architecture that built you spans billions of light years. This connection is not metaphorical, it is physical and historical, written into the very elements that constitute your existence. The awe you feel when looking at a starry night is not just wonder at a distant object. It is a recognition of home, a glimpse of the immense, interconnected neighborhood to which we all belong. The cosmic web tells us that we are not insignificant because we are small. We are significant because we are a conscious part of something so grand, so beautiful, and so vast that its full majesty may forever lie just beyond the edge of our understanding. These 28 secrets have taken us from the ghostly skeleton of dark matter to the faint, hot breath of the missing atoms, and from the frozen echoes of the Big Bang to the silent, growing voids. We have seen how this web is not a static monument, but a living, dynamic entity, still weaving itself together and actively shaping the fate of every galaxy within it. It challenges our fundamental laws of physics, feeds the most violent objects in the cosmos, and even mirrors the neural networks within our own minds. Our cosmic address, a quiet street on a minor filament, has granted us both the stability for life and the perspective to see this grand design unfold. This journey redefines our place in the universe. We are not just living on a planet, we are temporary, conscious patterns woven into the largest structure known to exist. Our very atoms are a product of its ancient gravitational currents. So tell me, which of these 28 secrets reshaped your understanding of reality the most? Share the one that truly amazed you in the comments below. This grand cosmic architecture does more than shape galaxies. It may also hold the ultimate key to life itself. The flow of elements and the stability required for biology are not random gifts, but consequences of our specific place within the web's universal design. On a planetary scale, we search for a Goldilocks zone, that perfect orbital distance where water can remain liquid. On a galactic scale, the cosmic web creates its own version of this delicate balance. A galaxy like our own, situated on a quiet filament, enjoys a stable, long-lived existence. It is far enough from the violent gravitational turmoil of the dense clusters to avoid being stripped of its gas or having its planetary systems disrupted by close encounters. Yet it is still connected enough to the web's rivers of matter to receive a steady, gentle inflow of hydrogen gas, fueling just enough star formation to replenish the galaxy without chaotic bursts. This sustained, moderate pace is crucial. It allows for generations of stars to live and die, forging in their cores and final explosions the heavier elements like carbon, oxygen, and iron. These life-giving elements are then scattered into space, eventually becoming part of new solar systems. A galaxy in a chaotic cluster might produce these elements too quickly, bathing nascent planets in deadly radiation. A galaxy isolated in a void might never produce enough of them at all. The web, through its large-scale structure, seems to naturally select for these cosmic incubators, these quiet suburban streets where the conditions are just right for the slow, patient chemistry of life to begin. The very atoms that form our world were likely delivered over billions of years, funneled along the dark matter highways that connect us to the rest of the universe. Our existence may not be a solitary accident, but the most intricate product of the largest structure we know, a whisper of biology emerging from the silent geometry of the cosmos.